Optimal energy estimation in quantum physics. The infinite square well challenge. Ooh, do we have something fun today? I'll break down the process of finding the best trial function to approximate the ground state energy of the quantum system, but how close do you think we can actually get? And guess what? You're going to need these two bad boys right here. And yes, they will be linked below because you will need them repeatedly throughout the rest of the course. Let's see what this question is. In problem 8.16, we're tasked with part A, use the function psi of x is equal to ax times parentheses little a minus x for x between 0 and little a. Otherwise 0, so we're actually a piecewise definition. To get the upper bound on the ground state of the infinite square well. Part B, generalize to a function of the form psi x is equal to a bracket x times little a minus x to the p power for some real number p. What is the optimal value of p? That's such a good question. And what is the best bound on the ground state energy compared to the exact value? Oh, this is going to be so fun. Okay, so why do we care? Well, this is a great approximation scheme using polynomials. Polynomials are typically easier to use than some combination of trig and exponents. And the challenge I have for you, and this is more of a metaphysical question, is how close can this method of approximation, the variational principle, actually get us to the actual answer? Sometimes exact, but is there some kind of rigorous way to show that there is a, precision to this method? I don't know, just a random question that keeps popping in my head. That being said, there is a PDF available to help you follow along, and I suggest that you grab it because this question is fantastic and utilizes things that are going to be useful later. So you may as well grab a copy of it, even though most of it is in the video, but there's still little bits that are kept out just because the algebra gets a little intensive. But, always good to have more than not enough. That being said, if you find value in this content, you can make a big difference by liking, subscribing, sharing it with a friend, or donating through Buy Me a Coffee. No account required. That being said, whole bunch of other words, but let's dive into this problem because I'm too excited. All right. Stop number one. As always, we have to normalize this trial wave function. Okay. So we set the square integral equal to 1, and we see that we're only defined from 0 to a. All things are real or assumed real, so we're just going to square everything. A-okay there. And then if we expand this out just like a typical polynomial, we can find the antiderivative really quick. Notice here that we have a squared, x cubed, a x fourth, and x to the fifth. So all terms have an a to the fifth that gets factored out. And then because everything has an x in it, the 0 term on the second boundary term goes to 0, so we don't really worry about it. But we simplify this to a squared times little a to the fifth over 30. And so we're just solving this down. Multiply the 30 over a squared, or a to the fifth over, take the square root, and we have our normalization. We're good to go there. So not bad at all, but let's graph it and see what this looks like compared to the actual solution to the infinite square well, and then we'll see about how close this actually looks like and why this makes sense. All right, so in the green dashed line, remember that the infinite square well solution was of the form square root of 2 over a, with a being the width of the well, sine of n pi over a times x. So this green line is a sine function that is restricted to 0 to a in the same bounds that we had for this piecewise function. And then the red line is everything that we're working with now. And as you see, it works pretty well. It's actually pretty well compared to the actual ground state. So we would expect that the energy bound should be pretty close as well. So let's see how close this actually is. However, the expectation value in this regime, remember that for the infinite square well, the potential is 0 inside the well. So the Hamiltonian composed of the kinetic and potential part, well, the potential goes to 0. So we don't care about it. Now we're just left with the kinetic energy operator, which is the second derivative, and a bunch of constants. So we can take the constants outside. We're left with the square on the inside. Cool, cool. The derivative does not act on constants, so we're fine. Well, assuming it's constant coefficient anyways. And now we're just left with taking the double derivative. So go ahead and dump that x into the parentheses to expand it. Then we see that we get, one derivative down, another derivative leaves us with a -2. That cancels with the negative and a 2 here after we simplify from the normalization constant substituted in. And now we see we're just left with a polynomial integral or integrand to integrate, so we can do that relatively quickly. And of course, if you don't remember where the forms come from, go back to equation 2.11 and 2.22, and that'll refresh you. But I think we've seen enough of that by now. All right, so find the antiderivative, not bad at all. Evaluate it again, a x squared, x cubed, so everything has an a cubed in it, which we factor out and cancel with the a to the fifth in the bottom. Good to go. Now we're just left with 1/2 minus 1/3. Find a common denominator, but that 3 cancels with the factor of 3 from the 30, reducing it to a 10. 3 minus 2 gives us a 1, and we're left with a 2 in the denominator. Cool, cool. To make a comparison to the ground state, we need to force in a factor of pi squared. We do this by multiplying by quote 1, but the 1 looks of the form pi squared over pi squared. So algebraically, we're good. That's the multiplicative identity for the reals. So we're good to go. And then we see that we get pi squared h bar squared 2ma squared. So that is the E1 for the infinite square well. And we see that our overestimation bound is 10 over pi squared. So putting this together with the equations 8.1 and 2.30, we see that we get the energy ground state is less than 10 over pi squared times E1, which is true. It is less than because of the 10 over pi squared. However, the 10 over pi squared is remarkably close to the actual ground state. So if we just find out what percentage it is, 10 over pi squared times 100% gives us 103 or 101.32% the ground state. So that's only over by 1.32%. And as we saw in the picture, that's really, we saw that the wave function was pretty close to the actual, or the trial function was pretty close to the actual wave function. So a 1.32% is really freaking cool. And it's, well within the 5% margin that we would have needed if we were using that margin. So that's pretty cool. And so the next part of this question is going to be, well, if we get really close with the power of this thing being to a 1, what is the optimal power to put this to? And that's what part B will be about. So let's get into that. So, as stated, we're looking for what if P was 1 in part A, what is the optimal power P to put this to? And with that, we're going to have to normalize this function just like we did before. So we have 1 equals a squared, again, just double it because of the magnitude squared. So we're fine, good to go, good to go. And now we see that we split up this bracket, so we have the form of the integrand, which is x to the 2p times a minus x to the 2p. And this is not just a normal integral. We have to use something that we can account for all p on the boundaries. And guess what? You're going to need some combinatorical nightmares, or that can possibly happen. And that's where the integral tables come in. And in this PDF, which is linked below, this handbook is going to come up over and over again. And like I said in the very beginning, you're going to want to reference this one, particularly 18.24. Okay, so this is going to be our hallmark guide to how to solve some of these integrals. So from 18.24, they state that the form here from 0 to a of x to the n power, parentheses with a to the n minus x to the n, all to the p power, is equal to this monstrosity. Okay, so we have a to some power, gamma function, gamma function, gamma function within right here. And so if we're just to form match this with what we have, the leading x here to the m power is 2p. So we say that m would go to 2p. Now, in the parentheses, we have something to the n, something to the n, but both of these have n equal 1 if we're comparing to what we have in our situation. Now, the outside is to p, but what we have is 2p. So what we need to do in form matching is say that p goes to 2p. Now remember, just because the labels or something does not mean that we have to do anything weird. We just have to look at what the label represents, and that's the total power on the parentheses. So although it's labeled the same, don't be too worried. Just use arrows like I have here, and then you can plug in accordingly. So with that, if we plug in the result from this integral table for what we have here and just simplify the integral down, what we see here is that we have a to the 2p plus 1 times 2p, and then gamma function, gamma function, gamma function, that all need to be simplified. Thankfully, n equal 1 means we're dividing by 1, so we get a gamma function compilation here that's pretty simple. Okay, nothing too crazy right now, but we're still going to be stuck with how do we simplify the gamma functions. Okay, so since we have gamma of 2p plus 1 here, times another gamma of 2p plus 1, that'll simplify to a square. We have 2p, 2p, that'll combine, and a 1 plus 1, that'll combine. And thus, we see a composition here of the gamma gamma, and we can call upon our friend, the gamma function, in terms of factorials to tell us what this is. Now this top one's pretty straightforward and easy. We see that we have the form of n plus 1, so we just get a 2p where n is 2p factorial. For this one, we're going to have to use our other friend here, which is a recursion relation, to push it forward and divide through, of course. And that gives us 4p plus 2 factorial over 4p plus 2. And then when we want to simplify for the a squared that we know we're going to need in the next step, then we can just go ahead and simplify this down and divide everything over to the one side. And thus we're left with 4p plus 2 factorial divided by, now that we see that we have 4p plus 2 right here, multiplied by the reciprocal, this puts us in this numerator. But since we're dividing by that, we put it in the denominator here. So that's the algebra that is shown in the PDF. But we can go ahead and leave this here, and we're good to go. Now, quick note on this. If we take the square root of both sides, and we plug in p equals 1, we actually get the same normalization factor as we did for part A. So that's a great verification check that we saw. And that was awesome. Let me just go ahead and write that. Part A, we had p equals 1, and this form checks for that, so you're good to go. That's a great little self-check, especially in trying to read the forms. Does it actually make sense for what we had seen before? That's a great little intuitive step. Now, moving on to the expectation value, we can use a little trick here. Of course, we saw that the potential here was 0, so we don't need to include it. We have the trial, and of course the potential energy term here. Take the constants out front. But what we notice is that this derivative, instead of acting on some general function twice, why not use the anti-Hermitian property of the derivative, which we showed was the case back in, I think, chapter 2, maybe chapter 3, and we showed that this was the case when we took integration by parts, and we put the derivative onto the other term. But because integration by parts has the negative, uv minus integral v du, the negative sign comes with it, and so we get a cancel, cancel, and now we have the derivative on the trial, derivative on the trial. So when we go to plug into the integral form for the inner product, we have derivative on the trial function squared. Okay, so instead of taking one thing, the derivative twice on one thing, we could take one derivative on both things and then square it. So that'll help us in our simplification. And that's what we're going to see here. Bring all the constants out front, distribute that x into the general form here. So we have little a times x minus x squared to the p power. And now when we take the derivative, it'll be pretty quick and easy, but remember, chain rule will come into play. So let's go ahead and get that simplified. All right, as stated, power rule, bring the p down. Ax minus x squared, p minus 1. That's just the power rule. Now the chain rule comes in, so we have a minus 2x, and then everything's in the magnitude squared. So from that, we square this p, which is just some real number, so that can be taken out front. That's the p squared. We need to square this parentheses here, so we have a minus 2x squared. Then we have this thing here that needs to be squared, but because we're multiplying 2 into this power, we distribute that, and hence the 2p minus 2. Now, because of the way that this chain rule happened, we can notice a derivative relation and thus a substitution. Looking via inspection here, we see that ax minus x squared parentheses 2p minus 1 in the derivative. If we take the derivative of this, then of course power rule, leave that alone, then chain rule on the inside, we actually have the expression here. That's what we have in the integral here. So the goal is to solve for this in terms of a derivative, and then from there, we can set up an integration by parts that moves pretty fast, thankfully. And so we solve for this by dividing this and this over, as we see here, and then we see that the green and green match, so now we could substitute this relation in and make our lives slightly easier. So substituting this in, since we already had a factor of a minus 2x, but that was a square, whenever we put the substitution in and we divide it by the same factor, that reduces this power to a 1, which is perfect. Since again, this is all constants, we can put it out front, no big deal. And again, all the constants that were on the original integral are now being forgotten for now. We're just focusing on how to deal with the integral that we have on our plate. Okay. And so integration by parts, with u being this first thing and dv equal this thing, well then v would just be the integral of both sides. Fundamental theorem would allow this to pass through, so we're fine. And so we have u, v at the boundaries minus v du, and we're good to go. Notice here that the negative and the negative sign cancel away, so we're perfect. And then we just have a 2 that comes out front, no big deal. Now, here on the boundary term, we actually evaluate to 0. And that becomes very helpful to us because of the fact that here we have a times x and then a minus x squared. So if I plug a here, I have a squared minus a squared, 0. And then if I plug in 0 minus 0, that's still 0. So either way, I get a 0. And that is wonderful. Okay, so we don't have to worry about the boundary term at all, and that makes our lives a whole lot easier. Now, in order to use the form that we had before, what we need to do is factor out the common x here after the integration by parts, and that puts us back into the bracket form that we had started with. Okay, but from here, we can split this up into 2p minus 1 on both of these terms independently, and that's what we see here. And then from there, we can use the same 18.24 from the integral table, except now this is the m that we had from the table. So m would go to 2p minus 1. The power on a and x are still 1. And then the power on the parentheses is 2p minus 1. And that's all summarized here. So now that we have all that, and we have this 2p or 2 over 2p minus 1 and the normalization factors, we can combine them all into one thing and actually simplify this down pretty quickly. So 2 over 2p minus 1, this is the form from the table here that we need to plug into. M plus 1 plus n times p, all the gamma, gamma, gamma within. Notice that the minus 1 plus 1 cancel everywhere. Minus 1 plus 1. Nice, nice canceling. We love to see it. 1 times the red thing is just the red thing. So we see that the power just reduces to 2p plus 2p minus 1. Again, all the gamma functions pretty much reduced down to some factor of 2p, so we like that. Simplifying it all to its furthest extent, we see that we get 2p plus 2p gives us the 4p minus 1, good to go. Now we have a square on the gamma again, and then gamma of 4p. So even if you wanted to use the forget the name of the identity here, but you can have gamma of 2x is equal to a product of other gammas, or you could just leave it like this. To evaluate these gammas, again, let's revert back to this. And here we see a very streamlined effect of this thing and this thing. So because here we have a gamma of 2p, for example. Oh, where's my pen? Right, if we're looking at, or just gamma of 4p, we're looking at this one. If we have gamma of, I don't know why I wrote f. Let's go back. If we have gamma here of n plus 1 equals n gamma n, but we know that gamma of n plus 1 is just n factorial. Then we get n gamma of n. I don't know why I keep writing f. Okay. And then we see that gamma of n from this gamma. Why do I keep doing that? I don't know. Some habits die hard, I suppose. Gamma of n equals n factorial over n. And that gives us exactly what we see here. N factorial over n factorial over n, and we're good to go. And that works for both of them. So we're in a great position to maneuver and simplify. We have everything in terms of, 2p and 4p and factorials. And if you remember anything from like power series and differential equations or calculus 2, we know that factorials can be simplified, but we might have to chug out a few terms. And that's what we'll see when we put this all together with the normalization found earlier. And let's see how this gets done. So the total Hamiltonian then, we have our p squared, h bar squared over 2m. We found that initially from all the integral constants and evaluating that inner product. Here we have a squared, and here we have what we just found. Okay, so I tried to color coordinate this across the board with what will cancel. Clearly the a and a go together. 4p factorial, 4p factorial, 2p factorial squared, 2p factorial squared, and then everything else that is not color coordinated is just random p's that need to be simplified. So stacking them like we would do in a ratio test, we see that the a's, the 4p and 4p would cancel, and we're just left with a -1 plus 1. See that there. Thankfully, the blue factors here cancel completely, so we're good to go. What a wonderful, nice cancellation. The 4p plus 2 factorial and 4p, we're going to have to do some work on that numerator. And then here, we see that we have all the leftover terms that we just need to be aware of. So with that, let's go ahead and simplify and plug out or chug out terms from this 4p. Remember that the factorial is just that thing times 1 minus that thing times that thing minus 1 again, repeating. So if we plug out or chug out two terms of this, we get 4p plus 2 times 4p plus 1 times 4p factorial. So that cancels with the denominator. Then this 4p plus 2 cancels with this 4p plus 2, which we see here. Good to go. We simplify the a's down like mentioned before. If we distribute this p squared into this, we get a 4p cubed. Then this 2p squared gets simplified to 4p squared. So 4 cancel. The cube up here gets demolished with the p squared down there. So we actually simplify this thing in a very simplistic manner. See the a minus 1 and a to the 1. That simplifies to a or 1 over a squared. So that's what we see here. We have our 2p from this and this that are left over. We have a 4p plus 1 from the purple left over. And then we have this 2p minus 1 right there. So all that crazy integration that I spent going cuckoo for Cocoa Puffs, looking up and making sure that we had the right values, trust the instinct, trust the math, and let that work itself through. And we see that we get simplified to actually something pretty nice. And again, P represents the power that the trial function should be to. And since P is the variational parameter in this context, we can optimize and find the minimum Hamiltonian by taking the derivative of this thing. And we see that when we compile this down into a simplified Hamiltonian, where we distribute the 2p and the parentheses here, we just get a polynomial over another polynomial. That's a rational function. So taking a derivative with respect to p, a quick quotient rule will simplify this down to 16p squared minus 16p minus 2 over the denominator squared. Again, the PDF has all the works on that and how to set it up, but quotient rule is what it is. You can use, do it brute force or do Symbolab or Mathematica. Does not matter. But all of that work gets simplified down into just a polynomial equation. And once again, we see that we have polynomials and quadratics. Very, very cool. All right, so now that we have the derivative, let's go ahead and set it equal to 0 and find the optimized parameter. So we have all our derivative equal to 0. So once we go ahead and take this, multiply it to the 0, take this, multiply it to the 0, what we're left with in actuality is the numerator equal to 0. But 16, 16, and 2 all have a factor of 2 in it, so we divide that out as well. And that leaves us with 8p squared minus 8p minus 1 equals 0. What comes to mind? Quadratic equation. Now we see that we get two potential roots for this polynomial given by this. Again, all the nitty gritties is in the document. And so we see that we actually have two roots. One that's 1.1 whatever, and then a negative. Okay, but which one is actually the minimum? Okay, well, we're going to have to use a derivative test here. Okay, so clearly with this one being a negative and this one being a positive, we could set up our number line as such. And with that, we see that if we use test values of -1, 0, and 2, right, then we plug in -1 to the derivative, we get a positive. Plug in 0, we get a negative. Plug in a positive, or plug in 2, we get a positive in the derivative. This tells us that we're increasing. Then we go to decreasing, then we go to increasing. And if that's the case, we have increase to decrease, so we have a mountain here, which means that we have a maximum. We don't want that. Minimum or decreasing to increasing, we have a valley, so we have a minimum. So we want to utilize P1 here. P2 is therefore extraneous and we don't want it. And in fact, if you plug in P2, what you're going to see is divergence in all the values. And it makes no sense that we want a negative P value for the polynomial. We want to match the sine function in a kind of Taylor series approximation way. So why would we want a negative value for the power? It would not make sense. So there's several ways to check and make sure that this is the right value. So utilize all that you can from calculus and actually get through with it. But now we're stuck with simplifying this thing. So you have 2 plus square root of 6 over 4. And we just have to simplify. Because we have a 2 and a 2 here, going back to the factored form, or the Hamiltonian itself, 2 cancels and reduces that 4 down, and then we'll see that 8 cancels after the square, and we can simplify this pretty quickly. All right, so those 4s reduces to 2s, so we're good there. After squaring, we get a 16 in the denominator, so that 8 and 16 reduce to a 2, which we see here. This 1, we need to find a common denominator with this one, so 2 over 2 will do. And now we can add all the fractions across the board. Top fraction, bottom fraction. We see here that we get 10 plus 4 square root of 6 plus 2 plus square root of 6. Easy enough. And then we see that we get 2 plus square root of 6 minus 2 over 2. So the red 2's here cancel. And then we have 2 and 2 here in the numerator canceling. Wonderful, wonderful. However, as math classes have taught us, we don't want that square root of 6 down there. We want a rationalized denominator. And so multiplying by 1 can help us get there. But here we also have to put in that pi squared factor like we did in part A in order to compare it to the ground state. So since we're multiplying by 1 anyways, just multiply by square root of 6 pi squared, top and bottom, and now maneuver it out. So this pi squared will go to this constant factor or constant fraction, which we see here. Put that all together, that'll be our E1. Now we see that square root of 6 gives us a factor of 6 down here. Pi squared stays. 6 and square root of 6 and 12. That gives us 12 square root of 6, but 12 is composed of 6 and 2, so I can factor a 6 out. Then my 5 square root of 6 times square root of 6 gives me 5 times 6. So I have a factor of 6 in both the numerator and denominator. So cancel, cancel. And thus, what I'm left with is 5 plus 2 square root of 6 over pi squared times our constants, which is pi squared, h bar squared over 2ma squared. And that is equal to our ground state for the well. Okay, but we're left with 5 plus 2 square root of 6 over pi squared. Now, this is remarkable because what we actually see is that this is 0.3% above the ground state energy. 0.3%. That is 16.4, I believe. Yeah, 16.4 times less error than the 5% error cutoff. I lied. It's actually 16.8% less. That is a miracle, and I freaked out in excitement about how close this actually was. And we saw how close p equal 1 was, and we could only guesstimate what would happen for p equal 2, right? But what we saw was that the square root was p equals 1 plus 1, 1 with some other digits. And let's take a look at how close this actually is to the actual wave function. This is for our optimized root. And you see, excuse me, and you see it's a darn near perfect reflection to the actual sine function. And again, if we know that we have something like this, where it's a sine and we want to approximate it using Taylor series, then we could go ahead and just chug out polynomials that have to be concave down. So we see that we get a form fit pretty well. And in the PDF, I just made this a Desmos link, so you can utilize the Desmos link and go tinker with it if you want, and check out how all the different styles of powers will work. I just made a slider for P, and in that slider you could see all the different ways that when P modifies, how it deforms from the sine here. And we see that P equal 1 is a good fit, but P equal 1.1237 is almost perfect. Of course, we see that it's 0.3% over, but that's really, really not bad, all things considered. And then you see a massive deviation when you get to P squared, or P equal 2, so the whole thing squared. That being said, very cool. And then to further increase our intuition here, if we had a negative power, that would blow up and it goes concave up, and we don't want that. We want to converge, not diverge. So very, very cool. Oh man, that was just an incredible problem and exercise, and I was very delighted to work through kind of the mathematical jungle. This is the first time we've seen the gamma function make an appearance with the integral tables and how to simplify that. This was a great approximation to the actual thing. So the power in this theory is wonderfully, for how simple it is to talk about, maybe a little bit of messiness in the actual execution. But for such a simple model, this thing has a very good amount of power and can help us approximate something to a very high degree of precision and accuracy. Again, 0.3%, are you kidding me? That's just amazing. So, you know, I'm going to do a couple more questions like this just to highlight the power, because who doesn't want to see more high precision approximations? And quite frankly, just more practice is going to help you regardless of what you study. And seeing forms, seeing functions, things like that. Always, always, always trust your mathematical instincts and check it with rigor because guess what? None of this stuff is easy to deal with.